Okay, class, this is a short introductory lecture to the concept of interval estimation. So far, we've been dealing with what we call point estimates, which are single value estimates of population parameters. So whenever we take a sample from a population and we observe certain statistics in there, those are just estimates of the population parameters, the corresponding population parameters. However, it is more than likely that that particular estimate is wrong. In other words, you won't get it exactly right. So what can we do about that? Instead of actually just using a point estimate, which we know almost 100% of the time, it will be wrong. In other words, it won't be the exact population value. Why don't we get an interval estimate instead? And with that interval estimate, we now have we could actually apply to it a level of confidence, the likelihood that that interval actually contains the mean. So the basic idea behind an interval estimate is that it is made up of two parts: a point estimate, right, and a margin of error. So if I say 10 plus or minus 3, that gives me from 7 to 13. That's an interval estimate as opposed to just saying 10. So as we mentioned here, we have a point estimate and a margin of error. That point estimate is usually what you get in the sample, for example, like an X bar, and the margin of error has two parts to it. It has the standard error and a critical value. And standard error. Okay. So in the case of estimating the population mean mu, we would take X bar, our sample estimate, and add and subtract to it a margin of error. Now, trying to get you to appreciate how we're going to create those interval estimates and interpret them, there are a couple of terms that I want you to think about. All right. One is called the confidence level or confidence coefficient. And that confidence coefficient is typically represented as 1 minus alpha. Alpha is the significance level, and that is really the fraction of the values that are not contained in the range that we are interested in. In other words, when we develop the interval estimate, if we attach a confidence level of 1 minus alpha to that, which is, let's say, as an example, 95%, then alpha, which is the 5%, is the likelihood or the probability that that interval estimate does not contain a population parameter. So alpha is really just the opposite. Not the opposite. How would you refer to that? Well, basically either you contain the mean or you don't contain the mean. So if the probability of containing the mean is 95%, probability of not containing that parameter, or the mean in this case, is 5%. All right. So one is a complement of the other. That's the term that I wanted to use. So here we go. To really kind of bring this into focus, I have to ask you to think back to the empirical rule. All right? Think back to the empirical rule. Now, you may remember with the empirical rule, we said if we believe that a sample that we obtained came from a normal population, right? And then we observe X bar and S. Then what happens is that we could take X bar plus S, plus or minus S, and 68.26% of all of the values in that distribution, or in the sample at the very least, should be in that range, right? X bar plus or minus 2S brings us to 95.44%, and then X bar plus or minus 3S to 99.77%. So that was dealing with the population. But what if instead we were dealing with a sampling distribution? where now instead of getting just x bar, we would get sx bar, where sx bar now is the estimate of sigma x bar, but we don't know exactly what sigma x bar is at this point in time. And then of course that's the estimate of mu. We know that. So the same concept applies. If I take x bar plus or minus 1 standard deviation, x bar plus or minus 2 standard deviations, x bar plus or minus 3 standard deviations. So that's the same 68.26, 95.44, and 99.77. But this time, instead of individual values falling in those ranges, it will be means, right? Falling in those ranges. And perhaps one of those means might actually be the population mean. So in essence, if we want to get an estimate for population mean mu, if we could generate an interval estimate from the sample data using this kind of concept, then we're able to get an interval that might contain the mean, and depending on the number of standard deviations that we use, that will give us our confidence level. So if we only use 1 standard deviation, our confidence level is not that high. It's 68.26%. If we use 2, it is 95.44%. And if we use 3, it is 99.77%. So these values right here, the 1, the 2, and the 3, are the critical values that I talked about. The critical value in the estimate right here. Where is it? The critical value, right? And then of course we need the standard error. The standard error is the SX bar. Now I'm using SX bar, not sigma X bar this time, because all I have is a sample standard error, not the population standard error. All right. So that is the, if you could understand or remember the empirical rule, just take that very same concept and apply it to sampling distributions. And if we apply it to sampling distributions, now we are saying those intervals will contain means, not individual values, but means, X bars. And one of those X bars might very well be the population mean. So therefore there is a chance that these intervals contain the mean, hence the idea of the confidence level. There's a 68% chance, a 95% chance, a 99% chance, etc. All right? So now we're going to formalize that and put it in an appropriate form for you. So in the case where we know the population standard deviation, sigma is known. The confidence interval is given by X bar plus or minus Z. So that Z is what we had 1, 2, and 3. That's a critical value. I'm going to use the notation of the textbook for now and explain why shortly. And we could use sigma X bar, but I'm going to go one step further now and replace sigma X bar with sigma over the square root of n. And that's because I'm expecting you to remember that a sampling distribution of the sample means has the same mean as the population. Mu X bar is equal to mu, and standard deviation sigma over the square root of n. All right? I need you to remember that. We're building on everything that we've done so far. So that's a case where it's known. So just bear with me, and then let's just look at the case where sigma is unknown. I'm going to have to introduce you to a new distribution called a t-distribution. And we'll come to that when I go through an example. What we will do now is that when sigma is unknown, instead of using Z as our critical value, we will now use a family of distributions called the t-distribution. And each t-distribution is linked to a degrees of freedom. That degrees of freedom is actually a function of the sample size. So rather than just a single distribution, which is the standard normal that we use when sigma is known, we now have to compensate for the fact that we don't know sigma, and instead of using a single value, we will use a distribution that also is symmetrical, but we have a family, and we would use a different one depending on the sample size. What's interesting is that the t distribution looks just like the normal distribution, but if you were to superimpose them, the t distribution tends to have longer tails and is much wider, whereas the normal distribution is much shorter, less variation, and taller. All right, so the two of them are symmetrical, but they're different, and so we have to use the t distribution when we don't know sigma. So t alpha over 2, and I'm going to explain alpha over 2 very shortly, bear with me. But this time we need something called the degrees of freedom to know which of those t distributions to use. The degrees of freedom for our case is given by n minus 1, and then we replace this instead of sigma over root n. Since sigma is unknown, we will use s over root n. So notice that the two formulas look very similar. This is your point estimate. This is your critical value, which is the t, and then this is the standard error. Point estimate, critical value, standard error. So they're quite similar. One when sigma is known, and the other when sigma is unknown. Sigma known, sigma unknown. Now, let's try to understand this idea of the confidence limit and the significance level. Remember, one is the complement of the other. So what happens is that the confidence level is really just the probability that that interval that you create is going to contain the population mean. So let's take this diagram here that we have in front of us, and we actually will pretend that we knew the population mean right here. So if I took a certain number of standard deviations, let's call it z for now, and added and subtracted that, that's my margin of error right there. However many standard deviations. Okay, remember in the empirical rule we use 1, 2, and 3 standard deviations. So in this case, we're not going to specify 1, 2, and 3 just yet. We're just going to say z as a, sort of like a default parameter to say how many standard deviations we're going to use. But that z will depend on the confidence level that we want. In other words, the space that will be occupied here and shaded in green. We call that 1 minus alpha, or the confidence level. So 1 minus alpha and so if I said to you I want 1 minus alpha to be 95%. In other words, I want 95% of all of the means to be in that range. I have to now go and compute what the z value is to know how many standard deviations I must use in the margin of error. Right? So remember, the margin of error is this piece right here, is the number of standard deviations that we're going to use to add and subtract to the point estimate. Z alpha over 2, sigma over root n. So if I specify my confidence level, I need to figure out how many standard deviations that is. In the case of the empirical rule, we specified the number of standard deviations, and therefore we then figured out what the level of confidence was. In other words, we said use 1 standard deviation, we will get 68.2. Use 2 standard deviations, 95.44. Use 3 standard deviations, 99.77. Those numbers aren't quite nice. So instead, we rather say, give me a 95% confidence level, not 95.44. or 99, not 99.77. In which case now we got to go back and figure out what those Z values are to use in the margin of error. Okay, so if 1 minus alpha is that green region and the diagram is symmetrical, what is outside of that green region has to be alpha, the remainder. So like 95% is in, 5% is out. 90% is in, 10% is out. 80% is in, 20% is out. But what is out is divided between the two tails. So since we know the area under the standard normal is equal to 1, if 1 minus alpha is my shaded region in green, therefore alpha must be the region that is outside. And since I have two tails, I must divide it by 2. So in other words, if 1 minus alpha is 95%, then 5% is out, but 2.5% will be in this tail, and the other 2.5% will be in that tail. So therefore, that is why we have the alpha over 2. And so the notation of Z alpha over 2 is just telling you that's the Z value, the Z value associated with having alpha on 2 in the tail. That's the area in the tail, right? So if I shade it in black here, that's the area in the tail, and that is the corresponding Z value. So that's just the notation that we're using in this case. All right. So let's kind of get a feel for how many standard deviations for different levels of confidence. Now, I'll be honest with you, we're not really interested in 68%. So we usually start at 90%. So let's look at 90% confidence interval. So if 1 minus alpha is 0.9, alpha would be 0.1. Alpha over 2 would be 0.05. And so now we want Z.05, the Z value associated with 5% in the tail. What's the fastest way to find that? If you look at this part right here, which is 0.05, if we look that up, we will get the negative Z value. And that negative Z value should turn out to be 1.64 or 1.65. Actually, each of them give you just slightly more or slightly less than 0.05. And so our textbook actually averages those two values and uses 1.645. But let's take a look. If you don't believe me, let's take a look. So I'm going to introduce the T tables in here. Or T tables and Z tables, sorry. Let's go start with the Z table. Okay, I think it's here. So we said that area in the tail was 0.05. Let's see where it is. 0.05. So we got to look in the body of the table to find it. And we will find it right here. 0.05. We'll find it right here. And if you look this up, you will see it is between 1.64 and 1.65. So what the textbook has done is to say, let's average those two values and use 1.645. You don't have to. You could use 1.64. I've seen some people use 1.65. But your book uses 1.645. They sort of in between those two, and so the Z value would be equal to plus or minus 1.645. So that's when 1 minus alpha is 0.9. The area in the tails would be 0.05, half of 0.1, and so therefore we would have a Z value of plus or minus 1.645. Let's look at it for the case when it is, let's look at the case where the 1 minus alpha is 95%. Let's take a look at that. So in that case, if 1 minus alpha is 95%, alpha is the remainder, 0.05, alpha over 2 is 0.025. So I'm looking for a Z value, Z of alpha over 2 is at 0.025. Look that up. So if I go to the tail, now I want 0.025 in the tail. Let's see where we find that. We find it right here, which gives us 1.96. So negative 1.96 on the left side, positive 1.96 on the right side. So therefore my Z value would be plus or minus 1.96. So notice how that's close to 2, but it's not exactly 2.0. When we said 2.0 standard deviations, we had 95.44%. But to get 95, which is a nice number for us to work with, we must bring the Z value down slightly to 1.96. Okay, so you could actually keep doing this. If I said an 80% confidence interval, a 90%, 92%, 94%, 98%, and so on, you could just do the computation. And in fact, we have a little table here that shows us, so our book gives us this. If it is a 90% confidence level, alpha is 10%, alpha over 2 is that. If you look up the area, you get 1.645. 95%, right? 1.96. And 99% is using 2.576. I would say 2.57 or 2.58, because when you look at those two values, you will get the same distance from what we're looking for. And if you average that to 2.575, that could work. All right. I don't think your answers are going to be that different if you use 2.57 or 2.58. And so I wouldn't worry too much about that. So those are very commonly used confidence intervals. 90% confidence interval, 95, 99. One of them is missing, which is 98. We also do 98. So in which case this would be 0.02. This would be 0.01. And then you look up the area of 98 or 0.99. And your Z value will turn out to be 2.33. That's what the Z value will turn out to be. So you certainly can keep those in mind for later use. All right. I've already mentioned, just to summarize, that the formula is X bar plus or minus Z alpha over 2 sigma over root n. This is X bar sample mean, confidence coefficient, the Z value, that basically corresponds to the area in the tail, population standard deviation, sample size. So we have that. We could certainly go ahead and do the problem. Let's do the case with the t distribution. What happens? Let's take a quick look. So in the case that sigma is not known, what do? We now have to consider the t distribution. And as I've already mentioned, the t distribution is really a family of distributions, right? And we see here a family of distributions, but each one of them is associated with a degrees of freedom. And the degrees of freedom basically is a function of the sample size. So this is kind of what it looks like. If this is your standard normal right here, the skinny one, the t distributions are shorter and they have longer tails, as I was telling you. So they look like a normal distribution, but they're shorter and have longer tails. And then as the sample size gets larger, the t values start to look very close to the z values. Okay, they begin to approach them. I will show you the diagram for that later, but I just wanted to show you the summary of what your confidence interval would look like. X bar plus or minus t alpha over 2 s over root n. Same basic idea as you could see, except that we're using t instead of z. And so to show you the table, so that way we could learn to use it. So the t-table from our textbook, we need to provide the area in the tail, which is our alpha over 2, and the degrees of freedom, which is actually n minus 1 for our case. So degrees of freedom, n minus 1, and the area in the tail, this is your alpha over 2 right here, those areas, and we'll get the t-values in the body of the table. So that table is a little different from the normal table. Normal table, what we're dealing with is that we have the z values on the outside and we have the area in the body of the table. In this case, we have degrees of freedom in one column, in one column, and then in the top row we have the area in the tail, and in the body of the table we have t values. So those t values are equivalent to z values. And the reason why this table is different is because now remember that you have a number of t distributions, not just one, a number of them. And so therefore we now have to kind of find a way to put as much information as possible on one page. So what we did was take fixed sets of areas in the tails, like if you have 20% in the tail, 10% in the tail, 5% in the tail, and then for the different t distributions, give you what the t values are. So that's kind of what has been done here. So every degrees of freedom represents a different t distribution. And for the area in the tail, for that t distribution, will give you the t values. All right? So we're going to work with that in a little while. So that's finding the confidence interval for a population mean with sigma known and sigma unknown. The last concept that I want to bring your attention to is the idea that we may want to find we may want to find an interval with a particular level of for margin of error, a particular margin of error. So just bear with me for a second. Okay. Just going to skip from my notes here to get to that section. Right, sample size. So what happens is that it's not uncommon when you're doing an estimate of a population parameter to take a random sample of a given size, say size n, whatever that is, and then we observe the sample statistic. And then if we happen to know sigma fine, we use x bar plus or minus z alpha over 2 sigma over root n, etc. But if we don't, then we use the t distribution. But what happens is that when we get the margin of error, remember the margin of error is well, let me just write the entire interval. This margin of error right here, if you notice, depends on a number of factors. One is sigma, z, the confidence level, and n, the sample size. So that's your margin of error. That margin of error determines how wide our interval is. And sometimes initially we may not be happy with the width of the interval. It might just be too wide to tell us anything. If I said to you that the average mark in statistics is between 40 and 80%, ooh, that's a wide range. But if I said between 70 and 80%, then you're a little more comfortable with that. So how do we get our interval to be small enough for us to make sense, but balancing with that the sample size that we need? So what we do in a case like that is what is within our control. Is sigma within our control? No. If we want a given confidence level, the z value is fixed. So the only thing we have left is the sample size n, how big a sample we take. And so for a specific margin of error, we could actually try to determine the sample size that we will need to get a particular level of precision. In other words, we specify the margin of error, and we'll say the margin of error is equal to Z sigma over the square root of n. And so now to get the sample size n, if we rearrange the formula and do the algebra, it will be Z sigma over the margin of error squared. All right, that will give us a sample size that we will need if we want to specify a particular margin of error. Now, in the case of the t-distribution, while the margin of error is ts over root n, we do not, and make a note, we do not use n is equal to t sigma over the margin of error squared. And why is that? The reason for that is because your sample size n will change. And if your sample size n will change, it means t will also change, because remember, there's a different t for each different degrees of freedom. And so you are using a value of t which is inconsistent with what the sample size is going to be, because that current value of t is based on your current sample size, but you're not going to get a larger sample size but using the same t value. So it's not appropriate to do that. So it's best to use something that is fixed, and so we always use this formula when we're finding sample size for a given margin of error to estimate the population mean. We always use this formula right here. Okay? Good. So having done that, I will do in a separate video for you an example. So that's just to give you the overview of an introduction to confidence intervals or interval estimation. And in this case, that is for a population mean, mu, when sigma is known and sigma is unknown. So next video would be a sample problem that is actually worked for you.